Okay, so here are some notes for you guys about sound. And this is part of the wave unit because sound is actually a longitudinal wave and it travels through air and most fluids. And what it really is the result of the wave disturbing the matter that it's traveling through. So if you think about a stringed instrument, the string goes back and forth with the wave, and in one direction, when it moves, it compresses the air, and in the other direction, it expands or stretches the air into the rarefaction. And when you hear sound, it's how our brain interprets that pressure wave that hits the eardrum. So like I said, it's a longitudinal wave, and this is what a longitudinal wave looks like, this little diagram here. So you can see the compression, and you can see the rarefaction where it's stretched out. And it's called a longitudinal wave because it travels in the same direction as the displacement. So it doesn't wave up and down or back and forth like the transverse waves. Since we're talking about sound, we need to talk a little bit about music. Makes some sense. Waves are what makes music. There's a fundamental frequency for each note that is associated with the longest wavelength that's possible to create in whatever the string or the tube or wherever you're creating this music. Harmonics are multiples of that fundamental frequency. So if you look at that first little diagram, the fundamental is actually the half wavelength. So it's from the first node to the antinode to that node that's in the middle of the diagram, because that's really the longest standing wave you can create in a string or a tube. Would be twice as long as whatever that is. When you look at it as the compression wave of that longitudinal wave, you get a picture more like the picture that is on the right, where those little dots represent air molecules. And you can see where there's a lot of little dots, it's the compression part of the wave, and where there's not that many, that's the rarefaction, where it's stretched out a bit. And nodes are the area where there aren't very many air molecules, and the antinodes are the high pressure areas where there are a lot of the molecules present. And since we're talking about sound, we need to talk a little bit about frequency. Each note has its own frequency, and it's the number of vibrations every second. And pitch is how we perceive those frequencies. So a high frequency we perceive as high pitch, and low frequency we perceive as low pitch. And the length of the string or the tube defines that fundamental frequency. And so changing the length or the tension of the string changes the frequency that's being played by a musical instrument. So speed of sound. Speed travels through air and liquid. It changes depending on how thick that fluid is that it's traveling through. So it will slow down in water, and it slows down when it travels through oil. It speeds up in a vacuum. The speed of sound in air is 331 meters per second at 0 degrees C. So it's a little bit faster at room temperature because it speeds up a little bit as temperature increases, because it depends on how thick the fluid is. And so the picture that I show there is kind of, my favorite thing about the speed of sound is the sonic boom, because it occurs when objects are traveling faster than the speed of sound, so traveling through air faster than the speed of sound, and it causes a buildup of that sound energy. And you can see the compression wave in the air when something goes by at the speed of sound. And the second to last little tidbit that deals with music is where the beats are created. And when beats are created when you have two different frequencies that interfere with each other. And that interference causes the waves to superpose and either constructively interfere or destructively interfere. And it causes that wah, 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 wah sound to happen. And when you want to find out what the frequency of those beats are, it's really nice and simple math. You just subtract the two frequencies. So if you can figure out the two frequencies, subtract them, you can figure out how often that wah wah is going to happen. Last one is the Doppler effect, and it's another thing that we hear. Fire engine goes by, and the sound from the fire engine appears to change. And as it goes by, the frequency appears to get higher, starts at a low pitch and increases to a higher pitch. But the frequency is not changing because the frequency is being emitted by the fire truck. If you're sitting in the fire truck, you don't hear that difference. If you're standing on the side of the road, you do hear that shift in sound. So there's some of the definitions that are kind of sound related, tying into the waves, tying into music. So I'll talk to you later. Bye-bye.